Hi, my name is Advay Paul and today I will be presenting our work titled Real-Time In-Sensor Computing and 8-bit ADC-less CMOS Sensing for Image Edge Detection. This work is done jointly with Samanvay Pal and Dr. Nirmay Modak from Jadavpur University. In this presentation, I will walk you through why in-sensor edge detection is important, the limitations of current CMOS image sensors, our proposed pipeline architecture for improved edge detection, and finally, the performance results that make this design stand out. We live in an age where IoT devices, edge nodes, and embedded vision systems generate enormous volumes of visual data. Most of this data is redundant and sending it to external processors, its latency, consumes power, and strains bandwidth. Traditional CMOS image sensors only capture raw frames. All computation, like edge detection or object detection, happens elsewhere in an image sensor processor or a microcontroller unit. This significantly slows down real-time applications like autonomous braking, robotics, and surveillance. In-sensor computing addresses exactly this issue. We process information within or near the sensor itself, reducing latency, power, and enabling faster responses. In an era dominated by AI and robotics, it's all about speed and minimum power budgets with broader vision applications. Our work focuses on real-time ADC-less hardware-generated edge frames directly at the sensor output. Before going into intricacies, we should highlight on some background and previous works. We have already discussed why we need in-sensor computing. Now, traditional edge detection methods like Sobel, Canny, and log provide good accuracy, but they require intensive digital computation. They depend on full-frame ADCs, frame buffers, and memory, making them unsuitable for small or battery-powered devices. Recently, hardware-friendly methods have tried using PWM pixels, TDC pixels, or compressive sensors. However, most of them either use high-resolution ADCs that increase power and area, cannot support high frame rates, or produce very low bit depth like 1-bit or 4-bit outputs. What is also missing is an efficient way to compare multiple pixel rows at the same time, since edge detection requires a local 3x3 neighborhood. So, the gap is clear. We need a high speed, low power, ADC-less design that can extract edges directly from pixel voltages without reconstructing the full image. So traditional edge detectors are low, slow, high energy overhead with external processing. Additionally, ADC consumes a lot of power, reduce fill factor, introduce quantization noise, and limit dynamic range. The core challenge is that conventional sensors operate sequentially, one pixel, one row at a time. This makes 3x3 window comparisons difficult in real time. Hence, our goal is to make something which bypasses the traditional full image reconstruction by detecting edges directly from raw analog pixel voltages, thus simplifying the vision pipeline. Hence, our objectives were achieve real-time 8-bit edge detection without using ADCs, extract edge information directly from raw analog pixel voltages via column parallel row-wise readout strategy, reduce power and silicon area using a counter-based time to digital converter, maintain high dynamic range and accuracy comparable to software algorithms, verify functionality via simulations and comparison. Here you can see the overall architecture. We use a 256x256 CMOS pixel array designed in UMC 180 nanometer technology node. Each pixel generates a PWM waveform proportional to its brightness. This PWM waveform is fed into a 3-stage counter pipeline which aligns pixel data from 3 consecutive rows. This is crucial because the 3x3 edge detection kernel needs access to 3 rows simultaneously, something normal sensors cannot do. After synchronization, the edge detection engine computes an 8-bit edge intensity for every pixel. The full system works entirely in hardware and delivers edge frames in real time. Each pixel is a standard 4 transistor CMOS pixel. It undergoes two main phases, reset and integration. During reset, the residual charge is cleared from the node capacitors, which are often parasitic, preparing pixel for next capture. During integration, the photodiode discharges based on the incoming light. This voltage is then converted into a pulse width modulated signal. Brighter pixels generate wider pulses. This time domain representation allows us to completely avoid ADCs. Instead, we use counters to convert pulses width into digital intensity. In later slides, we would see how we use counters to generate 8-bit quantized value from these PWM signals. Higher the pixel intensity, sharper the slope of VPD, which is the potential difference across photodiode. Longer pulse on time, thus leading to higher counter values. The heart of our design is the three-stage pipeline. In stage 1, a down counter measures the PWM high time and stores it in a PIPO register. In stage 2, an up counter regenerates the PWM of the previous row. This aligns the current row with the earlier one in time. A second up counter does the same for the row before that. With these three stages running in parallel, when the sensor is scanning row K, we simultaneously also have access to row K-1 and row K-2. This pipeline alignment enables real-time 3x3 window formation without memory buffers, the latency of only 2 times the row period, which is negligible at our operating frame rate. The edge detection architecture uses simple, efficient digital logic. For every 3x3 cluster, we take the 9 PWM signals to calculate local maxima or minima. Using OR, we find the pixel with maximum intensity. Using AND, we find the minimum intensity. Using XOR operations, we compare the center pixel with its local maxima and minima. From there, we compute the two counter difference. One is the delta I max, which is the difference between the maximum pixel intensity and the center pixel intensity, and the delta I mean, which is the difference between the center pixel intensity and the minimum pixel intensity. The larger difference among these two give the edge strength. This value is measured by a counter and becomes the 8-bit edge pixel. The entire pipeline ensures that new rows of edge pixels are produced continuously, enabling real-time operation. The entire pipeline and edge detection hardware was coded in System Verilog and simulated using Verilator and Spectre. The design sensor array is connected to pipeline through a common row line. The pipeline ensures that the pixel rows can be processed in edge detection hardware in complete parallelization. As we already discussed, the latency is negligible for us running a clock with time period in microsecond range. For every input pixel, we are getting an 8-bit edge pixel output, thus a very high throughput is observed. And since the design is FPGA and AC compatible, we can extend it to deploy using FPGAs or generate custom ASICs. Now coming to the key result. Our system achieves 651 frames per second, 60.1 dB dynamic range, total power 0.582 milliwatt at 0.65 volt operating voltage, figure of merit which is only 13.59 picojoule per frame per pixel, which is nearly 4 times better than the prior architectures. 8-bit resolution enabling higher sensitivity and stable performance under low light conditions. Importantly, the hardware generated edges match very closely to the software Sobel output, despite consuming dramatically low power. Here you can see qualitative results. The grayscale image is shown on the left and the output edge frames are shown on the right. The key observation is that the edges remain clear even under low illumination. This directly reflects the wide dynamic range, which is 60.1 dB in our case. Our software algorithm in MATLAB, RTL hardware simulation results all showed around 1.7% mean square error, which confirms that the hardware faithfully replicates the algorithm. This also validates the correctness of the three-stage pipeline and the edge detection engine. Additionally, the edge image quality does not deteriorate across different brightness levels, showing high robustness without requiring an external ISP. Compared with recent design from CEN, H.J. Kim, Park, Lee, and Zhao, our total power consumption is drastically lower for given sensor resolution and bit depth. Our figure of merit is the lowest among all compared works. Our design maintains 8-bit depth unlike earlier 1-bit or 5-bit edge imagers. Even at 180 nanometer, we outperform designs in 110 nanometer. And our frame rate of 651 frames per second is significantly higher than most hardware HD sensors. These results clearly demonstrate the advantage of counter-based ADC-less in-sensor edge detection. To conclude, we demonstrated a fully hardware-based 8-bit ADC-less image edge detector that performs real-time edge extraction inside the sensor itself. By leveraging time-domain pulse width encoding, our novel three-stage pipeline, we eliminate the need for high-powered ADCs and external image sensor processors. The system achieves 651 fps, 60 dB dynamic range, and extremely low energy per pixel, outperforming prior designs significantly. This work opens the door to new generation of compact, low-power, high-speed sensors suitable for IoT, robotics, and autonomous systems. Looking ahead, there are several exciting directions, like scaling the window size to 5x5 or 7x7 to improve accuracy, or reducing the process technology to sub 100 nanometer nodes. We can also integrate this sensor into autonomous vision systems. Achieving microwatt or nanowatt power budgets can be done using duty cycling and enabling reconfigurable kernels for different vision tasks. These enhancements will position the sensor as a self-contained edge intelligent device, ideal for next-gen embedded vision. And thank you for your attention. I will be happy to take questions.